All right, cool. Yeah, sure.
All right, everybody, we shall get started. So today it is our pleasure to have Angie Wolfgang visiting us from the University of California, Santa Cruz, where she's in her final year. And there's Greg Laughlin, which is going to tell us about sub-Neptunes.
Thanks, Linda. Yeah, so thanks for giving me the opportunity to tell you guys about this. I realize this is a little bit of an awkward time. But anyways, I'm really excited to be here and to tell you a little bit about my thesis work. So I've spent my thesis working with Kepler data, specifically looking at this extensive population of sub-Neptunes that Kepler has discovered. Kepler has done the hard work of detections, so the next step beyond that is understanding what these planets are, characterizing them. And so that has been the bulk of my thesis work. Okay, so my advisor at Santa Cruz is Greg Laughlin. So a lot of this work as well has been done in collaboration with a kind of like a working group that started at SAMC, at the Statistical Applied Math Sciences Institute. So they, every so often, they have these long programs where they bring in statisticians and scientists who are working in specific fields, so there's bioinformatics as well as exoplanets, is obviously the one I went to. And we just learn from each other. And so a lot of the methods that I'm going to be using and describing results from today, I learned at this workshop. And so definitely giving them credit for establishing such an awesome program. Okay, so to start out with, first the obligatory slide about the Kepler mission to overview what was going on here. So this mission, this telescope was in space. It stared at almost 200,000 stars over the course of 4 years. And what it was doing was searching for transits of sun-like stars by planets. So these transit signals are characterized by this dip. So if you're monitoring the star over an extended time period, then you can actually see that kind of that dip in the data. So the purpose of the Kepler mission is to explore the structure and diversity of the planetary systems. All right, so of course, one of the main goals of the Kepler mission was also to find as close to an Earth analog as we can get so far. But also in doing that, it has found a ridiculous number of planets. So it's very well posed to explore the structure and diversity issue. Okay. So throughout the talk, I'm going to be talking about observables and parameters. So I want to clarify from the outset what exactly I'm talking about when I say observables with respect to the Kepler mission. So the things that Kepler actually measures are the period of the transit signals. So that corresponds to the periods of the planet's orbit. And then also the transit depth, the depth of this dip that you saw up there. Okay, so there is a little bit of a fine point here. So the transit depth is related to the planetary radii, but through the ratio with the planetary, or through the stellar radius. So you have to know the radius of the star really well in order to be able to get out what the radius of the planet is. And that point, that fine little detail there is going to turn out to be really important, because it turns out that a lot of effort has gone into characterizing the stars that these planets orbit around, but there are still significant uncertainties on the stellar radii. And so that will come into play in a little bit. Okay, so going back to this goal, what is one of the overarching questions behind this goal is, well, what does this diversity mean for planet formation? So we've already had a little bit of a window into this kind of diversity through the enormous numbers of Jupiter-sized planets, or Jupiter-mass planets that have been discovered. So in 2002, the state of exoplanet detections was here. So there's about 50-ish planets on this diagram. I'm plotting orbital period and minimum mass, M Sinai. And so you can see that there were quite a number of Jupiter so super Jupiter mass planets at around 1-ish year orbits, and a few down here that were puzzlingly very, very close to their stars. So these planets could not have formed where we see them today. The in situ formation just isn't possible given the dust sublimation radius. They're well inside that. So a number of theories have been proposed to explain the existence of these hot Jupiters. I'm going to come back to that at the end of my talk. All right, well, a decade later, the situation for the Jupiters looked a little bit more like this. So this population is fleshed out, and as well as the hot Jupiter population over here. There seems to be a dearth of planets here, which is interesting. I'm not going to talk about that, but looking at these kind of diagrams, well, you have to be careful looking at these kind of diagrams because there's all sorts of selection effects and biases that come into play with these. But it's still quite interesting. Also, by a couple years ago, we had started to probe down to smaller mass planets. So there's this population of planets here that had started to emerge. However, it wasn't really until the Kepler mission released its data and its detections that this population really became evident how extensive that population is. All right, so this is what these are all of the Kepler planet detections in the first 8 quarters of data, so a little bit more than half of the data that we currently have. So again, I'm plotting orbital period here, but instead of mass, it's size. Since it's a transit mission, we're measuring radius if we know the radius of the star. Okay, so immediately the first thing that pops out at you is this huge population of planets that are between the size of Earth and the size of Neptune. Okay, so if you take all the planets in our solar system and you order them by size, there are no planets that fall in that range. There's a gap in our solar system. And it just so happens that there's something about the processes of planet formation that is very effective at creating these kinds of planets. Okay, so these planets have no analogs in our solar system by size, but also as a function of its period. All right, so all of these planets are much closer to their stars than Mercury is to the sun. All right, so these planets are unique in 2 ways. So characterizing them, these are 2 of the first questions that pop into mind when trying to understand these planets. So given that there's no analogs here, first, given that there's no analogs in size, what are they made of? What are these planets composed of? Are they more terrestrial like Earth, or are they more rocky, or are they more gaseous? Something like an irradiated Neptune. The other question is, how do they get there? How do these planets get so close close to their stars? So these 2 questions are 2 of the things that my thesis work is geared towards answering. Okay. So looking at the first one, what are these planets made of? All right, so to answer this question, what you usually look at is a diagram of planet mass versus planet radius here. So what's going on is that so all of the points here are measurements. These curves here are theoretical composition curves. So comparing a planet's mass and radius to these composition curves, which are derived from modeling the interior structures of these kinds of planets under a number of different assumptions, can give you a sense of what they could be made of. So just a note here that planet mass is a very difficult and expensive measurement to make. All right, so there's about 24 planets here that have, well, radius you get for free with the Kepler mission, because that's how we detect these planets. That's directly from the transit depth. But planet mass requires a lot of follow-up observations, either with rate of velocity, or if you're really lucky, then they're near resonance and you see transit timing variations. And if the transit timing variations have high enough signal to noise, then you could fit a degenerate model of mass and eccentricity. So even that's difficult. So we really don't have planet mass for the vast majority of Kepler targets. So 24 here, there are almost 4,000 planetary candidates that are Kepler sub-Neptunes. Okay, so in particular, I wanted to bring your attention to these two curves. All right, so this plot is courtesy of my collaborator, Eric Lopez. He graduated last year from Santa Cruz, and he's now at Edinburgh. So what he did was he modeled the thermal evolution of these planets given a rocky core and a hydrogen-helium envelope. So what he found is that when he incorporated the evolution of the planet, he found that these composition curves, a constant composition, are relatively insensitive to the planet mass. I mean, they're pretty flat. They're not perfectly flat, but they're close. Also, what he found was, I should explain what exactly this means. So 1% hydrogen helium means that the planet is made out, 1% of the planet's total mass is in a hydrogen helium envelope. All right, so this 1%, I'm going to refer to that as an envelope fraction later. So it's the fraction of the planet's total mass is in a gaseous envelope. Okay, so this is 1% hydrogen helium. This is 10% hydrogen helium. So the second thing that he found was that there was just a little tiny bit more of gas produced a large difference in radius for these sub-Neptune planets. So this is really exciting and suggestive. What this potentially means is that you get more information about a planet's composition just from its radius. That's where most of the information comes from. So you don't necessarily need given, if you assume this composition, a measurement of the planet's mass. So you can already gain some insight without going through all the expensive observations. All right, so given this kind of interesting result, what I was interested in doing is taking this insight and applying it to the whole population of planets. All right, so this kind of analysis has been done for lots of individual planets, but it's never been done for solving for the full population distribution of compositions. So that's the approach that I wanted to take. But in doing that, I needed to assume that all of the planets in this population were composed of a rocky core and a hydrogen-helium envelope. So the question is that a good assumption? Right, so you notice that there's another curve down here, or over here, pure water. So this is not a really physically plausible planet. It's one that doesn't have any kind of core. It's just a big ball of water. But it does give you a sense for kind of the limiting case if you had a water-dominated planet. And you can see that, you know, if you had a planet with a rocky core and a water-dominated envelope rather than a hydrogen-helium dominated envelope, there would be some degeneracy here with the smaller envelope fractions. All right, so why did we decide to go ahead and do this? Okay, well, you can make an argument looking at the extremes. Okay, so looking at these planets over here, these are well constrained enough, their masses in the radii, that they must be rocky. All right, and then looking at the other extreme, there are a few planets up here that must have some hydrogen and helium. There is no way that their large radii at their masses can be explained with just a water-dominated atmosphere. So looking at these extremes, what we decided to do was that, well, it looks like this rocky plus hydrogen helium envelope composition is reasonable to assume for the whole population, keeping in mind that there is this degeneracy. Okay.
It's a statement that the planets that have 4 Earth radii, they cannot possibly just be rocky and have like 60 or 100 Earth masses. That's the argument?
Oh, yes. Okay. So yes, that is also the argument, is that there are no 60 Earth mass completely rocky planets. Yeah. Thanks for that clarification. All right. So given this, we asked the question, what does the distribution of compositions look like? What is this distribution of envelope fractions? Why do we care about this distribution? Well, it's a really good test of planet formation theory, right? So for anyone who has a model simulating the formation of planets, one of the, in a bulk sense, one of the testable predictions is the distribution of compositions that you get out of your models. And so that's the distribution. Thinking about planet formation in a population-wide sense, that's a really important diagnostic for planet formation theory. And just to emphasize what parameter space we're looking at this low mass, low radius parameter space. It turns out this is where the enormous population of Kepler sub-Neptunes live. All right. Yeah.
The colors are different.
Yes, the colors are different compositions. Yeah, so this is also parameterized in terms of a rocky core and a hydrogen helium envelope. And the different colors is every 10% more of the planet's mass is in hydrogen and helium. Yeah. I saw another question? It was the same question. Okay. Thanks for clarifying. Okay. So going back to this idea with the theoretical mass radius curves. So given that these curves are relatively flat as a function of radius, and there's an enormous difference just between 1 to 10% of the planet's mass being in this gaseous envelope, the idea here is that you can take a radius distribution and read off the composition. Right? So this is the idea, taking radius as a proxy for composition. All right, so, okay, now that I've said that, then you can ask, okay, so why am I giving this talk? Why is this interesting at all? Why can't you just do that? Why can't you just read off the compositions? Well, the problem is that these planet properties are very uncertain. And the reason, okay, so what I'm plotting here is a histogram of the size of the error bar on the planet's radius divided by the radius measurement. All right, so the fractional uncertainty. And you can see that they're pretty significant. The radius bar can be just as large as the measurement, and sometimes even more. And the reason for this is because of the uncertainty in the stellar radius. All right, so so what we actually measure here is the transit depth. What we want is a planetary radius, but we need to know this very well in order to have good constraints on this. And the reality of the situation is that for the vast majority of Kepler target stars, we don't have very well constrained stellar parameters. People are looking at this, but these are somewhat on the faint side. And so it's taking a large observational effort in order to do this. So given this reality of the situation, we want to make sure that we accurately incorporate the uncertainties on these planetary radii into any analysis that we want to do, any insight we want to get into planet formation. Okay, this situation is very well suited to hierarchical Bayesian modeling. So this is a very natural method to use when you're interested in populations of things. I'm going to explain why that's in a second. And also if you have large uncertainties on your observables. And the reason for that is because in this framework you can marginalize over these uncertainties. And so you incorporate your uncertainty directly into your calculation. All right, so I really want you guys to understand what's going on here with what I've done. So I'm going to take one slide and just overview schematically what's going on with this method. All right, so to do this, let's start with regular Bayes. All right, so quote unquote regular Bayes. So this is the kind of thing that you would use, right, if you had a transit in your data and you wanted to fit different parameters. All right, so you have a posterior here. So this is the parameters that you're interested in given the data. And here's the likelihood, which relates the data to a model parameterized by theta. And then you have a prior on those parameters. Okay, so this is probably familiar to a lot of you. So this is Bayes' theorem. You can also express this graphically. And I'm going to be using these a lot, and you'll see why soon. So what we have here is the parameters. And so for all of these graphs that I'm going to show you, the parameters that I'm interested in are colored yellow. And then the data are the observables, are x. Okay, so the key here is that there is a probability distribution, the prior distribution on theta, and these theta are related to the data through the likelihood. So this is where the probabilistic relationship comes in. All right, so to make it a little bit less abstract, I'm going to show you how this looks for example compositions. Okay, so what we have here, these delta, that's the transit depth. So that's the actual observable, that's what Kepler actually gives you. What we're interested in here are the envelope fractions, this percent of mass in a hydrogen helium envelope. But it's mediated by all of these other parameters. Okay, and not all of these parameters are either going to be observed or the other possibility is that they've been measured but have significant uncertainties. So for example, you can see here that the stellar radius and the planet radius both factor into this. This would have significant uncertainty, so you need to marginalize over that. Okay. So so all of this is for one individual planet. Okay. You need, in order to do a good job at figuring out what's going on here, you need to include all of these things for each individual planet. But the question is, what if you don't just expect one true value of the parameter for all of the individuals in the population that you're looking at, right? Okay, so we're looking at a population of sub-Neptunes. We don't expect all of them to have exactly the same envelope fraction, exactly the same composition. We expect that there is an intrinsic distribution in that population. All right, and so this happens often in population studies. That's the situation we're in. All right, and so when this parameter has like the envelope, this parameter such as the envelope fraction has its own intrinsic distribution. This is where we take regular Bayes and make it hierarchical. All right, so what I've done here is a deceptively simple adjustment to Bayes' theorem, where still we have the posterior, we still have the likelihood. I've switched the excellent, this is still the data, sorry about that. So we still have the likelihood, and here we have a prior. But what I've done now here is introduced another distribution. I've introduced here. This is where this intrinsic distribution over the entire population plays in. All right? And so the graphical model looks like this. All right, so now what we're interested in is these population-wide parameters. For example, another example of when you want to use this is if you're looking at the mass distribution of planets that have been discovered by RVs, and you're interested in the power law index on that mass distribution. That power law index would be this population parameter. So you would use hierarchical Bayes for that situation too. Okay, so these parameters apply to the entire population. And they relate individually to every single planet, the individual parameters and the observables individually. So this rectangle represents this structure for every single planet. Okay? Now, the beauty of this extension of quote-unquote regular Bayes is that you can still use Markov chain Monte Carlo. All right, so the basic framework that you use to fit the parameters of your model to an individual set of observations can also apply to a population of observations. So you can think about this graphically, it's right here, as just adding another layer of probabilistic structure. Okay, so and I'm going to throw up our hierarchical model. All right, so again, what we're interested in, so this is very, very close to the map that I showed you, the graphical model I showed you earlier for an individual planet, where this is the envelope fraction of an individual. Now, here are the population-wide parameters that we are interested in for the distribution of compositions over this population. All right, so in case I'm a very graphical kind of person, so this makes intuitive sense to me, but I realize not everyone thinks in terms of pictures and graphs. So in case you are more of a equation kind of person, this is Bayes' theorem. All right. So you can see why, as soon as we go hierarchical, this becomes a natural way to display what's going on. So anyway, you can take a look at my paper if you're interested in how exactly I got to this point. Okay, so we're interested in the parameters defining the planet's compositions. All right, so the thing with this kind of map is that there's a relationship between, for every arrow, there's a relationship here. All right, so these are the population-wide distributions that we're interested in. Here we have the internal structure model. So this is where the theory comes in. And then we have this is where the likelihood is. So we've assumed a normal distributions, which is effectively like assuming chi-squared. Okay, now the beauty of this framework is that we're not necessarily tied to a specific internal structure model. We can, this is modular. We can insert anyone's, given your favorite internal structure model for these kinds of planets, and have a one-to-one comparison using the same exact data, the same exact statistical model, and see what is implied, what the differences are from your models to any other person's models. So there's real value in the modular kind of framework here. Okay, so well, now that we have our statistical model, we can execute this hierarchical Markov chain Monte Carlo. So specifically what we've done is we've used this software package called JAGS, which is written in R, which is a statistician's favorite programming language, just another Gibbs sampler. So you can check out details there. All right, so now we have the theory, we have our statistical model, now we need to define the data set. Okay, so the issue here, so just showing you the same period radius distribution. Whenever you are looking at phase kind of parameter space, it's really observable space here. These are observables, kind of. Anyway, you need to be very careful that you think hard about all the different selection effects and biases that you're looking at, right? You don't want to just take this distribution and try to infer things for your theory out of it. And the reason because of this is immediately obvious here as well. There's enormous detection bias in the Kepler planet detections. It is much easier to find a large planet in a small orbit than it is to find something out here. So any population study using Kepler planets, or really any survey in general, has to incorporate the numerous, these kind of effects. So extreme caution here. Okay, so the way that we addressed this, this necessary consideration is to very carefully choose our sample. All right, so hierarchical Bayesian modeling can also incorporate within this kind of statistical model that I showed you, these kind of selection biases. But we wanted to keep it as simple as possible at our first stab at this. So we decided to call our sample with some very careful cuts in the stellar sample in order to make sure that we were complete. All right, so what we're doing here is we're getting a complete sample. So what you're seeing is the radius histogram. So the salmon pinkish color, those are all of the quarter 1 through 12 planet candidates. So all of the planet candidates that have been detected in the first 3 years of Kepler's data. And then the blue here is the sample that we've selected to be complete. And specifically, the selection was like this, all right? So we did a period cut. So this was necessary because there's such a strong function. The selection function varies very strongly with period. But the rest of them were cut on the stellar properties, not on the planet properties. So we limited ourselves to a stellar sample that was the quietest stellar sample. Also observed all 4 quarters of the data that were available, and that had smaller radii. And the combination of these cuts allow us to be complete meaning that all the planets that are there we would have found, down to 1.2 Earth radii. So you can get a sense for what exactly happened in this cut by the black points. So the black points is effectively the completeness correction we've made by doing these cuts. So as you would expect, the completeness correction increases for smaller planets. Okay, so now that we now that we have a complete data set in hand, we can run the MCMC. Oh, I should explain why this is so important for what we're doing. So the shape of this radius distribution is encoded in the shape in the population distribution of the compositions that we're interested in, right? So because there's such a strong relationship between planet radii and planet compositions, we're using the shape of the radius distribution to inform what the composition distribution is. We need to make sure that that radius distribution is not subject to any of these systematic effects. All right, so that's why we care so much about this. All right, so you can run the MC and get some results. All right, so this is expressed in terms of Bayesian posteriors. All right, so what you're looking here is at these population-wide parameters that we were interested in. Okay, so this is the mean composition, and then this is the standard deviation of the distribution. So we assumed a log normal distribution. So we find, so this is the posterior samples, all right? So this, might not necessarily be that helpful for you if you want to actually know what the distribution looks like. So if you marginalize over all of this, then what you get out is this composition distribution, all right? So this is the actual distribution for these sub-Neptunes. All right, so you can see that it peaks around 1% hydrogen helium. And then the spread is about half a dex. So that corresponds roughly to the peak of the posterior. All right, so, and this encodes the shape of the radius distribution, as I just said. All right, so this is the first quantitative composition distribution that anyone has found for this population. If you remember nothing else about my talk, I want you to remember this. That due to this analysis, the results from this analysis is that about 1% of these planets' masses are in hydrogen and helium envelope on average. So this envelope fraction is the most likely composition for these planets. All right, so I've glossed over a lot of details. So if you're interested in the nitty-gritty of this kind of modeling, you can check out the paper there. This is percent.
Oh, percent.
Yeah. Thanks. Thanks for pointing that out. Yes.
So this is for all the planets.
Okay. So I should clarify that my sample, you could kind of see from the radius distribution. I'm only considering planets between 1 and 4 Earth radii.
Okay, but so this final result is for all the planets between 1 and 4.
Yeah.
But so you wouldn't expect
less than 25 days.
Yeah.
N period is less than 25 days.
So the thing is, we know that there should be more gas in the 4 Earth radii planets than in the 1 Earth radii planet.
Yep.
So when you set that result, I mean, it's marginalized over the radius of the planet. So, I mean, what does it really mean? Because if you have way more planets that have these 4 radii, you will be biased. I mean,
well, so that's right. Okay, good. I'm glad that you asked that because that's exactly what I'm about to address right now. Okay, so what I just showed you were the population results. So one of the benefits of hierarchical Bayesian modeling is that you also get information about the individual planets for free. All right. So if you want to know something about the population, you also get out what's going on with an individual planet. Okay. So if we didn't do this kind of modeling, if you really did try to read off the compositions directly from the radii, this is the kind of thing that you would get. All right. And so to address your question, what's going on here is the mean of that population distribution. It peaks at about 1%. because there's a large number of planets here between 1 and 2.5 Earth radii. You're completely right that if there were a large number of planets out here, that population distribution would reflect that in the data, because that's what the data would be telling us. But that's not what the data is telling us. Anyways, okay. So instead, rather than just trying to read off the compositions from the radii, yeah?
This one, okay, so just to be sure, because, so this distribution that you're seeing is actually not a distribution of the composition, or in a sense, it's a distribution of the type of planets that you have. You're just saying that you have more Neptunes, I mean, you have more planets with such mass in this range of radii, that you have planets bigger or smaller, but you're not saying at one mass we have a logarithmal distribution of planets,
yes.
Some are gaseous, some are rich.
Yes, this is not a function of mass, but the very next project that I'm going to tell you about addresses that. Yes. So yes, that distribution does not fold in information about the planet's mass. Yeah. Okay. So what we get, because we can actually, okay, so I threw up our model again here because you can see, so this is a planet radius. This is a parameter in our model. All of these white ellipses are parameters that we have marginalized over. So given the large errors in the stellar radius, there's also large errors in the planet radius as well, and we can marginalize over them. So this is what it looks like. This is an honest view of the things that you can infer from Kepler radii. All right. So you notice there's large errors here on the radius of the planet. Not only are they large, but they're asymmetric. All right, this is what makes it so difficult to accurately incorporate the large uncertainties in the stellar radii without going to this kind of sophisticated statistical modeling. So specifically, what I've done here, there's likelihoods that were produced by Dan Huber and the Stellar Properties Working Group at Kepler, and I've incorporated them directly into these simulations. Yeah.
So is the assumption you're making, so is the assumption that the errors, the uncertainties, and the stellar sizes are all uncorrelated with each other?
Oh, from star to star, you mean? Yes. Oh, yeah. That's definitely.
Good assumption, right? I mean, so is the uncertainty due to modeling uncertainties for the stars?
Huh. Okay. So okay. So the paper. Okay. So the likelihoods that I'm using were derived as part of this paper that Dan Huber wrote. He fits the observed photometry for these stars to stellar evolution models. So whatever systematic effects and offsets are in those evolution, I think he used the Dartmouth isochrones, I don't know. Anyways, but whatever systematic biases there are there, we also have here. So
Right, yeah, so the danger of doing hierarchical inference,
yeah.
is that correlated errors, if treated as being uncorrelated, they will usually bias your inference.
Okay. Yeah. So the problem of one star's properties being correlated to another star's properties, in my statistical model, I assume that they're not correlated. The treatment in the stellar properties paper was also that they're not correlated, individual stars between each other. So I don't think that that's necessarily a bad assumption. I mean, in fitting. Yeah.
The origin of the uncertainty due to modeling uncertainty, or instead is it just due to like poor measurements of the problem?
Okay. All right. Sorry, I misunderstood your question. So yeah, the width of this is due to the poor measurements for the photometry and fitting the different stellar parameters to the photometry.
Models applying the same data would give like the same.
Yeah. So yes. Okay. So the uncertainty due to the actual measurements is much larger than the model uncertainty for these stars. For these stellar parameters. Okay. So Okay, so the uncertainties in the planet radii also correlate or relate to produce uncertainties in the envelope fraction, the composition that we are concerned with. But even still, you can get a sense for a rule of thumb here. All right, so these uncertainties are large, but it's not hopeless. So if you see a planet that's between 3 and 4 Earth radii, assuming this kind of rock plus hydrogen-helium composition, you can think of it as being a few percent, the envelope fraction being a few percent. All right, between 2 and 3, the envelope fraction is about 1%. And again, because there are so many planets here, this is why this composition distribution peaks right around 1%. Okay, and then less than 2, the envelope fraction is about less than 1%. We also model the transition between rocky and planets with this kind of gaseous envelope. We incorporate a prescription for photoevaporation. It's pretty back of the envelope. So that part can definitely be improved. But the good thing is that we find that this transition is centered at about 1.5 Earth radius, which is fully consistent with some work that Leslie Rogers has done looking at this transition, incorporating mass measurements in addition to radius measurements. So we're definitely on the same page as far as that's concerned. Okay, so getting back to your question about, all right, so we have a distribution, but there's no mass measurements incorporated here, right? Okay, so going back to this plot, it is what we want to know, often is the case, especially for dynamical studies, right? We have Kepler radii, but if you're doing any kind of dynamical study, you want the mass. So we need a way to go from radius to mass, right? So looking at this kind of plot, it is really tempting to fit a line straight through it. I mean, people have done that. So in particular, Lauren Weiss and Jeff Marcy did that earlier this year. So they fit a power law to that, and you can see their data there. So what they use for the mass measurements are some very large, very uncertain radial velocity measurements. They're constraining, but it's still quite large error bars. Anyways, so this is the mean relation. So I'm going to refer to this as the quote-unquote mean relationship between a planet's radius and a planet's mass. Okay, so this is what it looks like plotted here. But you can immediately see already that there is significant intrinsic scatter here around the mean relationship. And this intrinsic scatter is also very interesting physically. We want to understand this intrinsic scatter. So one of the implications from the composition work is that you would expect this intrinsic scatter if indeed these planets have this rocky plus hydrogen-helium composition, because these planets' radii are relatively insensitive to their mass. Right? So if you're looking at a planet radius, it could have a large range of masses and still be at that radius. So you would expect this kind of scatter given that composition. So what we want to do now from more of a practical observational approach is to characterize this spread, so that we really can go from radius to mass, incorporating this intrinsic dispersion that nature is giving us. All right, so if we don't incorporate this kind of dispersion, then we're biasing our dynamical measurements to only be the average. All right, so it depends on what you want to do, whether or not that's okay. But if you're really interested in probing the full parameter space of your dynamical modeling, you want to incorporate everything that we know about a planet's mass as a function of its radius, if you want to use the Kepler planets. All right, so instead of thinking about this as a relationship, what we really should be thinking about it as is a probability density function. All right, so at a given radius, what is the probability that a planet has a given mass? Okay, so this is one way we can do it. So this is the mean relationship. I have some parameters here, the constant, the normalizing constant in the power law. What we want to do is go from here to this kind of probability distribution, where the mean is this power law relationship, but there's some intrinsic spread. All right, so let's consider what's going on with the data. Okay, so large uncertainties in both the mass and radius still exist. Okay, also, these parameters characterize the population. They're population-wide. We want one estimate, or really a posterior, for these parameters over the entire population. So again, we're set up to use hierarchical Bayesian modeling. All right, and so this is specifically the model that we're using. So we're using the data here are the masses, and we're relating them to the radii through these parameters. Okay, so these are the results that we get when we do this. So here what we have is we're plotting the normalizing constant and the power law index. All right, so these are the two parameters that Weiss and Marcy also fit for. So we have a posterior distribution. Weiss and Marcy have a point estimate. Thankfully, they're consistent with each other. They're definitely within 1 sigma error of each other. So that's encouraging. Means that, you know, we're not, our methods are consistent with each other, even though we come from completely different methods. Okay? But not only that, but we're also can look at infer what the intrinsic dispersion is. All right, so that's what the x-axis is. And you can see from the posterior that 0 intrinsic dispersion is excluded. It's excluded quite significantly. All right, there really is some intrinsic dispersion for these planets' masses at a given radius. Okay, so given these posteriors, if you find the mode of the posteriors, then this is the PDF that you want, the probability density function. All right. So if you are interested in taking the Kepler planets and turning them into masses for whatever study you want to do, this is the relationship you want to use. Okay. So what this means for the actual sample that we use. Oh, I should mention that the comparison with the Weiss and Marcy work, we use the exact same sample. Because we wanted to do an apples-to-apples comparison. All right, so the black data, the black points are the data in this sample. This red line, that's the mean relationship right here. And then you can see the scatter in terms of the red points. All right, so now we have a way to map radii to masses that accounts for nature's intrinsic dispersion. Okay, so I have a whole nother project that I could talk about, but we're almost at 5 o'clock now. Do I have until 5:10, or is it till 5 o'clock?
Yeah, and we'll ask questions through 5:10, so we're going to take another 5 minutes.
Okay, all right. So I'll outline this real quick. Thanks for asking all those questions. Made this talk pretty interactive. Okay, so now I've been spending this whole time talking about what we can infer about these planets from their radii. Okay, well, what about what's going on with their periods? Okay, so I'm interested in asking and answering this question: how do they get so close in? All right, so this is a huge question. There's lots and lots of work going on here. So I focused on just one aspect of this. All right, so I'm gonna zoom through this. Right, so there's migration. That's one explanation for how they got so close in. But also high eccentricity migration, and there's a whole bunch of different mechanisms for this kind of So with the high eccentricity migration, the idea is that something kicked this planet into high eccentricity, and if the periapse is close enough, then tidal forces take over and dissipate energy from its orbit. So there's a whole bunch of different ways that people have proposed to actually kick this planet into a high eccentricity orbit to begin with. So the one that I have been looking at for this project are these Kozai oscillations. I'm not going to explain what's going on here in this for the sake of time. But the idea here is that it's been invoked to explain hot Jupiters, which tend to be alone. So why couldn't they explain Kepler's singleton Neptunes, right? Okay, so if you look at the multiplicity of Kepler planets, there is a very large number of single planet systems, even more than you would expect when you count for the geometric probability that the other planets did not transit in that system. Even when you account for that, there's still a large number of these singletons. All right, so I'm gonna skip this. The idea here is that the time scales are not too different between hot Jupiters and singleton Neptunes, given our result from the composition work. So since our results, I mean, it seems to imply that these sub-Neptunes are mostly rocky, 99% rocky, then they could have significantly lower tidal Q values than what is often assumed for hot Jupiters. So even though the tides involved in this mechanism are a very strong function of the planet's radius, these lower Q values produce perhaps not unreasonable timescales for circularization. Okay. Now, the reason why I've chosen to focus on this mechanism in particular is because the key to this mechanism is the distant companion that causes these oscillations between eccentricity and inclination. And unlike planet-planet scattering, these companions are still bound to the system. They're still there. They're potentially able to be found. Okay, so what I decided to do because of this is to use adaptive optics to search for these companions. So I'm looking in particular for stellar companions. There's other people. I saw there's an email that got sent out. Heather Knudsen is visiting at the end of the month, so she's going to tell you about the RV side of looking for these companions as well. Okay. So again, I'm gonna skip this. The point is that I got almost 30 nights over the last 3 years at Lick Observatory at the Shane meter, 3 meter, using laser guide star adaptive optics. This is cool. This is actually the laser. We're looking at the Kepler field over here. What I did was I focused on these single Neptune systems using a multi-planet system control sample. So it turns out that the science here is very complementary with just the regular follow-up effort that has been done getting AO images of the Kepler targets. Because I mean, these systems tend to be fainter, and they're also lower priority for the other follow-up missions. Okay, so given that, I've observed just about 200 Kepler objects of interest, so these planet candidate hosts. And this is preliminary results for a third of the sample. And I should mention that the majority of this work done so far has been done by my high school students. I had a high school student this summer, very talented, and I'm very proud of her. She actually is a semi-finalist for the Siemens competition for high schoolers. Anyway, so she's very motivated. She got these results for a third of our sample. So looking at the magnitude difference between the central target star and any additional source in our field, and then the distance between them. All right. So what we find is that the fraction of planetary systems with additional sources within 2.5 arc seconds is about 20%. So this is fully consistent with what previous AO surveys have found. So a lot of the other than RoboAO, the other surveys have samples of about 100 KOIs. Okay, so the people doing these AO surveys have started to look at the relationship between this kind of stellar multiplicity and different parameters of the planet. All right, so this is a RoboAO paper. So their goal is to actually look at all of these stars in the optical. We're doing IR, so we're more sensitive to lower mass companions. So they separated their sample out into the giant planet, small planet. So this is the analogous line that relates to our sample. So they're finding, about 20%, maybe a little less. So that's good. So it's consistent with what they get, and this fraction is relatively constant too. All right, so that's fine, that's good. But what we're actually interested in is looking at the period distribution of planet periods. So this distribution, this is what will help us disentangle some of these different evolutionary effects, right? So you would expect that a different mechanism for getting these planets into high eccentricity orbits, would produce different eccentricity distribution, and potentially at the end, a different period distribution. So this project is still definitely in its infancy. There's a lot of work to be done on this. But this is where we're going with it. We want to actually look at quantitatively at the distribution of planet periods. All right, so this is my last science slide. Okay, so this is what we're looking at. All right, so this is the cumulative distribution of the planet period. So each value here is the number of planets in our system that have a period, that value, and less. Cumulative probability distribution. All right. And we've split our sample into 4 groups. All right, so we're looking at single planet systems versus multiple planet systems, and then we're also looking at systems that are where the star is isolated versus where another source has been detected in the field by AO. All right, so that's 4 groups here. So specifically, what this one is comparing the single planet systems to the multiple planet systems when there was another source that was found there. All right. So this is the comparison that gives power to insight into the Kozai mechanism, right? Because the Kozai mechanism requires this presence of this other companion, and we wouldn't expect that to operate for multiple planet systems because of this high eccentricity stage. It would have destabilized any other planets in that system. So we wouldn't expect the Kozai mechanism to occur for multiple planet systems. So what we're testing for is differences in the final period distribution between the innermost planet of the multi-planet systems and the single planets. And so we use the KS test. So with a p-value of 0.15, it's not statistically the null hypothesis. We can't reject the null hypothesis. So right now, statistically, these distributions are effectively the same. So right now, with a third of the sample, it seems like Kozai cycles maybe are not the dominant cause of single Neptune systems. But there is some other very interesting things that come out when you compare the other samples against each other. All right, so what we have here, again, these are cumulative period distributions. Okay, so just looking at the single planet systems where it's isolated versus where the star is potentially a binary, where another source was detected. So these distributions are marginally significantly different from each other. All right, and then over here, it's the same thing but for the multiple planet systems. Even for the multiple planet systems, there seems to be a systematic difference in the period distribution for the innermost planet here. And it's not really clear to me what's going on here. I thought about this a little bit. I'm convinced that there's a hidden variable in here, right? So not all of these sources that we find in our AO images are actually bound companions, all right? So that's part of the work that still needs to be done on this. So what can correlate with the presence of additional companions well, there's a correlation between that and galactic latitude. So there might be systematic differences in the properties of the stars here. So I have yet to look at that and figure out what's going on. But in any case, this is interesting. It's intriguing, and it definitely merits follow-up work. Okay. So future work on this project, there's a lot to be done. I gotta analyze the rest of my sample. This probability of companionship, really have to incorporate that. Okay. And integrate simulation. So given the constraints from the observations, simulate what exactly would happen with these Kozai oscillations and see whether or not tides could have actually kicked in here. And then integrate all of this. All of this is from a probabilistic framework. So the idea here is to integrate into a similar statistical model as what I was talking about earlier in my talk. To answer the question of what is the probability that the Kozai mechanism could have operated, either on an individual level or on the population as a whole. All right, so that's where this project is going. All right, and so I'm going to throw out my implications, and thank you for sticking around and listening to my talk.
Thanks, Angie. Questions?
So your mean mass radius relation is
So yeah, so we fit it as a power law, but it turns out that the exponent is roughly around 1.
So, as a non-planet person, so is that surprising or interesting or?
So yeah, well, okay, yeah. So what this is, right, so what this is saying is that there is a distribution of density as well. That's incorporated here. So personally, this is kind of more of like a practical thing where people want masses from Kepler radii. I don't think this is the best way to gain insight for what's going on with these planet compositions. I think what's better to do is to do this kind of explicitly incorporating the theoretical models and seeing and relating it directly to the data, kind of like what we did up here. So that's a more straightforward approach to get insight into, okay, well, how exactly do these densities vary? But I mean, it does. I mean, it's interesting for kind of qualitatively, I guess.
The physical insight.
Yeah, I mean, this is where the physical insight comes from.
One of the problems is that in one photo you want to describe solid planets without atmospheres, miniatures, and even part of the giant planets where, for example, you could have no variation of radius with mass.
They're not getting up to those sort of large radii yet, right? That for Earth radii.
I mean, we can, it's definitely possible to do this with a sample that goes out to larger radii. I mean, that's completely feasible, and that's one of the things that we're doing as we're writing up this paper. Yeah, I mean, so I've definitely started thinking about this population in terms of 1 to 4 Earth radii. Whether, I mean, you can argue it's kind of arbitrary, but from the Kepler period, from the Kepler distribution, it really does look. I mean, so there is negligible difference in the detection bias between a planet that's over here and a planet that's over here. And it really does seem to be this physical drop-off up here at around 4 Earth radii. There's something going on here about planet formation. So this is really interesting. So I mean, anyways, this is why I've started thinking about 1 to 4 as the population of sub-Neptunes, because of this really suggestive drop-off.
I have a question. What do you make of that 1% hydrogen helium envelope that you got? Is that surprising? Do we have
It is.
how you could make a planet like that?
Yeah, it is kind of surprising. Leslie Rogers had a paper about outgassing, what outgassing could produce for these sub-Neptunes. And if I'm remembering that paper correctly, she's getting envelope fractions of about a couple %. So it seems maybe that outgassing might be coming into play there. But I mean, these protoplanetary disks, they're complicated systems. And there's a lot of theoretical uncertainty about this. I saw a talk by Jonathan Williams at Hawaii. He looked at the gas-to-dust ratio for less massive stars, and he found that it's more around 10 than it is around 100. So I mean, there's something might be coming into play there. Yeah, there's a lot going on. It's definitely interesting.
So the final thing that you mentioned, about these companions.
Yeah.
So I was wondering if it's possible to measure proper motions to confirm the companionship.
So that's hard. People have tried and given up a couple of times to do this for the Kepler stars, but there's definitely a group at Space Telescope that is working on a proper motion catalog for the Kepler target stars. It's hard because these stars are so far away. So I mean, Kepler was a statistical mission, but at the same time, yeah. So I mean, it makes it very difficult. But people are trying. So honestly, that keeps me in business, because whenever measurements are difficult, it means there's going to be large uncertainties, which means that we need this kind of modeling in order to actually get some real insight from what's going on. So I'm okay with that situation.